On the way. Air commit raise. Okay, there we go. All right, so here's the warm up. Anybody watching along at home, go ahead and pause. Try this one. What you didn't see is we did go over number 8 from the worksheet. So if you're struggling with this, that's okay. Just try to follow along here and see if you can catch on. All right, so let's talk about it, everybody. Where is this positive? Where is this positive? Nathan, what do you think?
When x is greater than -3, or when x is less than -5.
Good. When x is, I would write it, x is less than -5, x is greater than -3, but that's completely fine. You said the same thing, just reordered. Okay. Now, how did he find that? Well, think about it this way. If I've got my highlighter here and I highlight all of the positive pieces, I'm highlighting here, I'm highlighting here, everything above the x-axis. So it's everything below -5 and everything above -3. Okay? That's where it's crossing the x-axis. At -5 and -3. Okay, well that must mean everything else is negative. So if I go to highlight here, all of that is negative. Everything in blue is negative. How do we represent that? Solomon?
-5 is less than x, and x is less than -3.
Good. -5 less than x, less than -3. Very good. That bounded region, right? Got boundaries. Everything in between there. Now, so that's positive and negative. Let's talk about increasing, decreasing. Let's talk about the roller coaster. Whoa. Talk about the roller coaster guy. All right. So when I go to highlight, where is it increasing? Okay, there. That's when I'm going up the hill. How do I represent that? How do I represent that? Yep. Right, but how do I represent in terms of the inequality? When is that happening? When is it increasing? Where does it start increasing? X equals what?
-4.
Good. So everything above -4. Is that right? He's good. Now, if it's not increasing, then it's decreasing, right? So therefore, this is all decreasing. The yellow there is all decreasing. How do I represent that? Well, that's just to the left of -4. Everything to the left of -4. Okay, what's happening on either end of this? What's happening on either end of this? Solomon? Good. So what do I write on each blank? Good. Feel a little bit better at that? I know this is still difficult. That's okay. I'm not looking for everybody to master this right now. This is just an introduction to it. Remember that later on you will cover this in great depth in Algebra 2. Right? You'll talk about end behavior a lot in Algebra 2. And increasing, decreasing, positive, negative, and all the implications of it as well. All right, let me ask you this. Are there any other questions on the homework that you'd like to go over? You know, I know we've already gone through 2 of these whole increasing, decreasing, positive, negative, all that stuff. So maybe, are there any questions on 1 through 4? After you're looking at the key, Solomon? 4. Number 4? How many x-intercepts do we see? How many times does it cross the x-axis? 3 times. Once, twice, 3 times. So where are those points? Well, let's list them out. 1, 2, 3. Okay, now remember, for x-intercept, they always have something comma y, comma 0. A number, comma 0. X, comma y. So this one looks like it's at -1, -2, -2.5. This one, oh, right at the origin point, 0, 0. This one, 1, comma 0. And then my y-intercept, oh, where does it cross the y-axis? Danielle? At 0, 0, look, it crosses at the origin point. Yeah, your x-intercepts and your y-intercepts can match if it goes through 0, 0. All right, let's get to our guided notes for today. Now, let's talk about where we're headed over the next couple of days. Today, we're going to start in on section 3.3. Now, in my mind, section 3.3 is going to take us a couple of days. Today, we're just going to do the introduction to it. We're just going to get like the first half of section 3.3 done. And it's not really, this is more like the easier stuff out of section 3.3. Tomorrow is a late start day, don't forget. You guys get to sleep in a little bit. I don't. That's okay. Get to develop professionally. Tomorrow is a late start day. We're not going to have a full class period. So what we're going to do is we're going to start in on day 2 of the notes for section 3.3. We're just going to get to whatever we can get to. We're just going to plug away and see where we can get with the day 2 notes of section 3.3. We might not get very far. We might get pretty far along, but we're definitely not going to finish all of section 3.3 day 2. That means, and I can't believe the words coming out of my mouth, it's not meaning homework tomorrow night. I don't know who I'm becoming. I don't know. I feel like I'm getting soft in my old age.
You're becoming
So tomorrow night, there's not going to be any homework. Okay? There's not going to be any homework tomorrow night because we're going to be finishing the notes that we start tomorrow. We're going to be finishing those on Thursday. Now, on Thursday, we're going to have a homework assignment due Friday. But then Friday, because it's the end of the 9 weeks, we're going to do this thing it's called the quarterly checkpoint. Okay? That's what we're calling it, the quarterly checkpoint. It's basically a test that every Algebra 1 student in the entire building can take. And it's just a test to see where we're at. This is not a test that will go in the grade book, but this is a test that we will grade to see how you're doing. Okay? It's not going to affect your 9 weeks grade, but it is going to be graded to see how you're doing and to see, okay, are we progressing enough? Okay? Are we doing what we need to do to get far enough along so that when it comes time to take your state test in April, are we where we need to be? Obviously, because it's called quarterly checkpoint, we're going to take one at the first 9 weeks, and then we're going to take the one at the end of the 9 weeks, and the second 9 weeks, and we're going to take one at the end of the third 9 weeks. We're not going to do a fourth 9 weeks one because we'll have already taken the state test by that point. But this is just to see where we're at, to see if we're doing the right things. And this is going to be taken by all of my students, all of Mr. DLAP students, all of Mr. Spollison's and Mr. Rutan's and Mrs. Apple's honors Algebra 1 students as well. Every Algebra 1 student in the building is going to be taken on the same day to see where we're at, to see if we're all progressing in the right direction. Okay, just trying to get a gauge on, okay, how are we doing? Are we covering what we need to cover? Are we on the right track? Basically, that's going to be on Friday. Approach it as if this were almost like a math test. Okay, you want to do your best on it. Okay, you want to do your best, as best as possible on it. Okay, that's what we're looking to see, because it's really for our data to see. Okay, are we on track? Are we doing the right thing? And again, the nice thing that comes out of it for you is that since there's no lesson on Friday, there'll be no homework over the weekend.
Yeah.
No.
Not the deal.
Yes, Frank.
So let's say theoretically, if I wasn't here Friday, when would I take it?
We'll just have you make it up another day.
I'll be there Friday. That's it.
Theoretically. Just asking for a friend. All right. So let's get to section 3.3 day 1. Let's get this out of the way first, though. Now, what we're going to be looking at now, we were just talking about in section 3.1 and 3.2, general functions. Like in section 3.1, we defined what a function was. We said these are the parameters that it's got to meet to be a function. And then we took it a step further and said, okay, if we know it's a function, can we identify domain? Can we identify range? And then we started identifying weird things that are going on in the graph, like is it increasing, decreasing, positive, negative, end behavior, all all that fun stuff. Where are the x and y intercepts? All of that stuff that we've done so far. Now what we're going to do is we're going to hone in on linear functions, just linear functions. So what is our definition of a linear function? It's just basically a function that forms a straight line. I know it seems pretty simple and pretty self-explanatory. It's a function that is a line, but really it's a function that can be written in the form y equals mx plus b. Does anybody remember what that's called?
Wasn't it like
You want to help?
I remember like the y-intercept thing, but I know that.
Oh, you're close. The slope intercept. It's called slope intercept form. We have y equals mx plus b. Slope intercept form. Slope intercept form. Now, if you can write it into slope intercept form, then it's a linear function. The graph, wow, mind blowing here. The graph of a linear function is a line. I know. Don't let that throw you off. I know it's hard. I know it's difficult. Oh, man. Likewise, a linear function is just a function that's linear. Let me ask you this. Are there any linear functions, or excuse me, I said it wrong. Are there any linear equations that are not functions? Are there any linear equations that are not functions?
Probably, but
Probably. That's a great answer.
I have like a really strong feeling that like there is like linear equations that aren't linear functions, you know.
Okay. Do you have an example of one?
Oh no.
Oh no, he's just saying yeah.
I
He's just saying probably. Thank you.
Doesn't y have like a classical number or something on them?
Oh, okay. So I like that. What we said, if it's got an exponent. Well, if it's got an exponent, it would no longer be linear, and we'll talk about that by the end of the day today. We're saying, okay, just a straight line function. If it's got an exponent, it curves, so it's no longer linear.
Would it be if it crosses with another one?
We're talking about one equation.
Okay.
Let me ask you this. Why is this blue line a function? If I asked you to explain, what would you say? Good, it passes the vertical line test. Good. What about, what was that? I know. Came from the back table. I try not to pay attention to what happens at the back table. Does that pass the vertical line test?
No.
No, it does not. If I draw a vertical line on that, does it hit more than once? Yeah, it hits an infinite, it hits at every point, right? It hits infinitely. So therefore, is that a linear function? No. It's linear, but it's not a function because it doesn't pass the vertical line test. So yeah, there's only one type of linear equation that's not necessarily a linear function. And that's why we define a linear function to be any non-vertical line. To be any non-vertical line. A linear function has a constant rate of change. Does anybody know what I'm talking about when I use the term rate of change in terms of a line? People, that's slope. That is slope. When you talk about the rate of change of a line, you're talking about the slope of that line. So we're saying any linear function has a constant rate of change. Therefore, any nonlinear function just is not a line. Okay, bear with me for this next example. It's going to be rough. It's going to be way more difficult than anything we did yesterday. Is that a line?
No.
So we say that this is a non-linear function. Now, I described it as a function. Did I correctly describe it as a function? Does it pass the vertical line test? Yes, it does. So therefore, it is a function. So I called it a non-linear function. Guys, if it's linear, it's just a straight line. Okay. So, okay, here we go. Is that a straight line?
Yes.
Very good, boys and girls. Very good. So we say that this is a linear function. You know, it says to explain. Do you know what's hilarious about that statement that you just said right there? I looked in the book to see what are they getting at? Like, what do they want us to say? It says, yes, it's a linear function. And the explain was, it's a line. It's like, oh wow, that's groundbreaking right there. That is just, it's a line. Okay.
Wow. That sounds like an answer I would do.
Right. Okay. Really quickly, is C linear? No. Is it still a function?
Yes.
Yes, it's just not linear. So we would say C is a nonlinear function. Is D linear?
Yes.
Yes, linear function. Does that make sense?
Yes.
So I think it's very easy to tell from a graph if something is linear or not. So flip it over onto the back when you're ready, and let's talk about it in terms of tables. There are a ton of questions on the OST that gives you a table and says, what type of function is this? So you have to decide, first off, is it linear? As we learn new functions, we will do the same thing. Is it linear? Well, to see if it represents a linear function, what you're looking for is a constant rate of change. You're looking at a rate of change for your x's and then a rate of change for your y's. So let me ask you, how much are your x's changing in this case? Nathan?
They're adding 3 every time.
Okay, so let's write it in. We say that this is going plus 3, plus 3, plus 3. So what I see right now is a constant rate of change for x's. Let's see if I have a constant rate of change for y's. Well, I go down 6, down 6, down 6. Is it a constant rate of change for my y's?
Yes.
Yes. So I can call this a linear function. We can call this a linear function. Now, for the explain, I do need you to explain. What is the explanation then? The explanation is constant rate of change for both x and y. Constant rate of change for x and y. Because it could have a constant rate of change for x, but not for y. Or a constant rate of change for y, but not for x. So it's got to be a constant rate of change for x and y. Guys, do you know what we're examining here? We're looking at the slope. That's really what we're looking at here. We're looking at the slope of that line to see if it's a constant slope. Take a look at the second table. What are my x's going up by? 2.5. Going up by 2.5. Let's see if that pattern continues. Okay, yep. Okay, yeah. So, do I see a constant rate of change for my x's? Let's see if I've got a constant rate of change for my y's. Is this linear?
No.
No. But you may be thinking, well, I see a pattern. Those are all going up 4, 7 to 11, 11 to 15. I agree with you in that, but that doesn't make it linear. What that makes it is actually quadratic, which we'll learn in the next chapter. So we say that this is nonlinear function. Now, why is it not linear? Well, because how do we word this? Nonlinear function because the not a constant rate of change. That's it. Not a constant rate of change in the y values. Not a constant rate of change in y. You have to tell me which one makes it not linear. What negates it from being linear? Is it the x values or is it the y values? Okay, take a look at the next table. Do I have a constant rate of change for my x's? Yes. I'm going up 2, up 2, up 2. Do I have a constant rate of change for my y values? No. I go up 26, then up not 26, whatever that is. 98, right? Does it really even matter at that point, though? No, because once I see that it is not the same number, you can say that it's not linear. It'll matter later on when we move past linears. It's not linear. It's still a function. Okay? It's a nonlinear function. And what makes it not linear? Not a constant rate of change. Where? In y. Good. Not a constant rate of change in the y values. So let's take a look at our last one here. First off, is it a constant rate of change in x? Yeah, it's going up by 2's again. Is it a constant rate of change in y? Yes. I'm going up by 9, by 9, by 9. Good. So this is a linear function. And how do we know that? Because it's a constant rate of change. In x and y. Gentlemen, be quiet back there. You're always talking. I'm going to make you sit in like different corners of the room. Like you're too. Questions about that? Now, when you're looking at the equation, so what did we look? We looked at graph, we looked at table, now we look at the equation. Guys, it's easier for me to tell you what can't happen than what can happen. Basically, what you're looking at in the equation is like nothing weird is happening to x. Like it's not in any square roots, it's not squared, it's not in any exponents, it's not multiplied with y, it's not multiplied with another x value, it's not in an absolute value. Nothing weird is happening to it. But what happens if it's not even there? Like y is equal to 3.8. Let's take a look at our first one here. Y is equal to 3.8. Is that linear? Well, let's kind of examine it. No matter what the x value is, the y value is 3.8, right? That's what my equation is telling me with y is equal to 3.8. Like if x is 1, y is 3.8. If x is 2, y is 3.8. Except if x is 3, y is 3.8. So what's happening there? Well, if x is 1, it's 3.8. If x is 2, it's 3.8. If x is 3, it's 3.8. What type of line am I making? What type of line?
Horizontal.
A horizontal line. A horizontal line. Is that a linear function? Yes. So if you ever have a y equals, I'm going to circle all the linear ones. If you ever have a y equals, that's a linear function. It's a horizontal line. If you ever have an x equals, that's a vertical line. And are vertical lines linear functions? No. They're linear, but they are not functions. Okay. What about my middle one here? Is that linear? No. Why not? Because of the square root on the x. So if I were to explain this, I would say, no, not linear, square root. What about my last one for that set? 3 to the x power. Why not? Because the x is an exponent, right? We will eventually call that an exponential equation. We study that in like March. Take a look here. What about y is equal to 2 over x? You want to know what this is going to look like in the end? Take a look at this. Watch my graphing calculator here. 2 over x. You think it's a straight line? Oh.
How did you do that?
Yeah, that's some cool stuff. Why don't my calculator do that?
It's called graphing calculator. You know, you get these in algebra too. But is that a straight line? No. So what was weird about that? What was weird about that?
It goes from negative to positive.
Right. But in terms of the equation, how would I tell just by looking at the equation? Good, yeah, because it was divided by x, that piece right there. All right, y is equal to 6 times x minus 1.
No.
I could put it in the calculator again. But take a look here. If I just distribute that, it kind of looks weird because I've got a 6 on the outside. But if I just distribute it, is that linear? Is there anything weird happening to x?
Yes.
What's weird?
Then it's being multiplied by 6.
Well, if it's being multiplied by a number, that's just is the slope. And that's just my y-intercept. So this is linear. This is linear. All it's doing is being multiplied by a number and then subtracted by a number. Now, is my last one linear? No, because I've got an x squared, and that cannot happen.
I think I just went 1 for 6.
You want O for 6 there?
Oh, for sure.
All right. So that's the lesson for today. That's where we're going to stop today. Tomorrow we get into like actually graphing word problems as well. Right? Actually taking the word problem and putting it on a graph. So that means that you're going to need your graph paper starting tomorrow. Okay.
I just put it below. I have a really hard.
All right. So long, everybody at home.